Welcome to Cinemeric Live, application technology made simple. Our video series presents Cinemeric topics in a practice-oriented way and will take up just a few minutes of your time. Today's topic, thread milling. Thread milling involves various manufacturing processes which will be covered here in detail. And of course, we will explain how these processes are implemented in Cinemeric Operate, with a practical segment threading on the milling machine included as usual at the end of this video. We would also like to refer you to our video Basic Principles of Thread Types and Their Production, in which we took a detailed look at the definition, classification and primary functions of threads. The opportunities presented by threading include thread milling and tapping, both of which we will view again live in our practical section, and for the sake of completeness, drill thread milling. All manufacturing processes are included in Cinemeric Operate. Thread milling is a cutting process which is an extremely cost-effective way of machining threads. This is also suitable for internal and external machining, where we have the choice of using single-edge or multi-edge milling cutters. The diameter of the tool, the general size, is therefore relative to the thread diameter being machined. Consequently, larger threads can also be produced, for example, with smaller thread milling cutters, or smaller threads with larger thread milling cutters. This allows us to maintain flexibility. The helical travel path is characteristic for this manufacturing process, where the tool is inserted from the top down during milling or from the bottom up according to the pitch of the thread. The standard cutting process for female threading is tapping, also commonly referred to as thread cutting. The corresponding, in other words the correct, profile tools or the appropriate taps are required here for each thread size. We must consider two different types of drill holes here, the blind hole thread and the through hole thread. The blind hole thread stops at some point within the material and the chips must be conveyed upwards with the corresponding tap. In the through-hole thread, the chips can be conveyed downwards. Preliminary drilling of a tap hole, in which the thread can then be cut, is an essential requirement for this option. Meticulous synchronization between spindle and feed rate is also of utmost importance during this process. The pitch, therefore, then constitutes the feed rate for each rotation. Another cutting process for female threading is what's known as drill thread milling. This process combines multiple machining steps in one. Cinemeric Operate also offers a cycle which is provided precisely for this purpose. As the name suggests, drill thread milling drills and mills the thread in a single pass. So we do not need a prepared tap hole or a core hole for the thread. Instead, the tool drills into the solid material, prepares the tap hole, then immediately cuts the thread and creates the corresponding thread chamfer. It's imperative here that this tool is supplied with a coolant from the inside so that the cutting edges are precisely cooled while at the same time discharging the chips. This produces a large number of chips. And here too, however, increased tool wear occurs. We also require sturdy clamping of the tool and a stable machine. In preparation for our practical section, we'll take a quick look at how we access the respective machining input screens for the manufacturing processes. Thread milling can be found under Milling and then Thread milling. The opened cycle screen for thread milling allows the option of selecting and deselecting the female thread or male thread to be produced. Female and male threads are not shown in separate screens, but rather on one screen together. Tapping can be found under Drilling, tapping using the respective parametric preselection options. What is important here is that thread forming is implemented using the very same screen. Likewise, there is no separate screen provided for a different manufacturing process. Both these processes are included in a single screen. And drill thread milling, also to be found under Drilling and Drill thread milling. Here again, the technology-related values are entered, enabling the thread to be produced as a result. And now to the practical section. This is the practical part which we'll be manufacturing today. The following manufacturing technologies will be applied: milling of a female thread, drilling of threaded holes, and milling of male threads. What does this now look like in detail? The individual machining steps are structured as follows: face milling of the surface and drilling of the threaded tap hole for the female thread and milling of the outer contour. The necessary thread chamfers are then added and the female thread milled. We now switch to machining of the holes, in other words, point machining for drilling the threaded holes, and then the 4 threaded stems are produced. How are the individual machining steps represented on the control unit? After configuring the unmachined part, we immediately begin face milling to acquire a clean and parallel surface. Following this, external milling is then performed around the outside to depict the outer contour, and the tap hole diameter is prepared in the next stage for our M32 by 1.5 thread. This diameter totals 30.5 mm. Since the formula for calculating the core diameter is nominal diameter minus pitch, so 32 minus 1.5 equals 30.5 mm diameter. Following this step, these contours, which we refer to as islands, are milled. The material on the edge between these contours is removed fully automatically using the pocket milling function, leaving behind these 5 islands: our threaded cylinder with the individual future threaded bolts, which are currently merely cylindrical ridges. And after milling, the thread tap hole diameter of our thread M12 is machined, i.e. with a twist drill. In this case, a solid metal twist drill that goes through the material in one pass and generates a diameter of 10.2 mm. M12 minus 1.75, tap hole diameter for M12, 10.2. After drilling, we must chamfer the tap hole diameters, because the thread chamfer protects the future thread so that the first burrow is not damaged and the mating part can be screwed in correctly. It also removes any burrs, because sharp edges are created when cutting metal, which are then removed in the process. And in precisely the same way as the chamfering on the tap hole diameters is removed, the chamfering must also be removed from the ridges, the future M10 threads, as well as from the M32 by 1.5 thread, and naturally from the outer edges of our workpiece. This is achieved by chamfering in milling mode with a 45-degree chamfering bit, which removes the sharp edges cleanly and completely. The next step is tapping. The M12 tapping in our pre-drilled tap hole diameter. Once here in the middle of the M32 by 1.5 and the 4 holes arranged in the circle. After selecting our tool in the tool menu, here we set the thread which we would like to produce, in this case an isometric thread. Alternatively, we can of course also opt for the Whitworth pipe thread, UNC thread. Of course, it's also possible to work without the thread table. In this case, however, all values must be entered manually, The tabular selection enables fixed presetting of the pitch, thus allowing us to cut the thread using different technologies. So what do we mean by different technologies? Either in a single step through the hole, in and out in one stroke to complete the thread in its entirety, or to avoid any chip congestion by applying what's known as the chip breaking method. The tool is inserted a certain distance, stops briefly, and then is turned back a short distance before continuing into the thread. The chip removal cycle functions somewhat more efficiently. The tap is inserted into the material, then completely removed again, goes back in and out again until the final thread depth is achieved. Here too, as already mentioned in the theoretical part, synchronization of the spindle and the feed rate permits repeated insertion into the thread. Thread milling is initiated following completion of the tapping. In this case, we'll start with the M32 by 1.5 thread. The thread milling cutter is selected from the tool menu, the required cutting speeds are set, and we are now provided with the range of options referred to in the theoretical section. With thread milling, we have the option of cutting the thread either from the top down or from the bottom up. This means the tool starts at the bottom and finishes at the top edge. Sometimes this is necessary for technological reasons. Of course, we also have the option here as to whether the machining setting should entail a left-hand or right-hand thread and, significantly, female or male thread. All three of these variants are incorporated in a single cycle. Multiple cycles are not required. There are so many options included in one thread milling cycle that a single cycle is more than adequate for all selections. In this case, quite clearly a female thread. The M32 by 1.5 thread is a fine thread rather than a standard thread. It's not possible to select our isometric table here simply because the thread is not featured in the pull-down menu. We therefore select No Thread and enter our values pitch 1.5 and consequently nominal diameter 32 as the diameter. This concludes the setting of all values. H1, for example, is the flank height of the threaded tips, which is calculated automatically and entirely independently by the system for technological reasons. As is the case for the large thread, it is totally irrelevant for the cycle whether a large thread or a small thread is involved. RM10 is the same technology, except here we use the isometric table to select the thread, and M10 is of course a standard thread. Needless to say, this has already been stored and all values are entered fully automatically. Following completion of these program sequences, we now check our overall program with the simulation which is identical to the control unit. Then we can begin the manufacturing process. The user-friendly cycle screens combined with a realistic simulation suitable for production guarantees the user a fast and reliable process for thread production with Sinomeric Operate. Thank you for watching and see you next time.
Siemens, ingenuity for life.